Hello guys, welcome to another video of the course. In this video, we are going to solve the problem number 5 and so on from the chapter 2. Let's see how many problems we can solve today. So, the problem 5, a coil with 100 turns is connected to a 120 volt 60 hertz power supply. If the magnetizing current is 5 amps, calculate the following. A. The peak value of the flux. Phi max. The peak value of the magnetomotive force. The reactance of the coil Xm, the inductance of the coil Lm. So we have one coil, the number of turns, the voltage, frequency, and the magnetizing current are given. So let's calculate these parameters. To calculate the phi max, the maximum flux in the core, we can use this equation. Yes, we used this equation multiple times before. The RMS value of the coil voltage is equal to 4.44 Fn phi max. So if you replace numbers here, we can calculate the phi max as follows: 120 divided by 4.44 times 60 times 100. That is equal to 4.5 milliweber. This is the maximum flux in the core, right, for this coil. The part B, the peak value of the magnetomotive force. You know that the peak value of the magnetomotive force is corresponding to the peak value of the magnetizing current. Yes. So the RMS value of the magnetizing current is given here, 5 amps. So we can calculate the peak value of the current. You know that the peak value is equal to SQRT02 times the RMS value. Yes. So, integral of H dot dl is equal to Ni, the maximum. The peak value of the magnetomotive force is peak value of this product. So this is 100 times I peak. So if you replace the numbers here, 100 turns times SQRTL2 times 5, this is the peak value of the magnetomotive force. So consider these terms, the phi max, peak value, right? Otherwise, you calculate the numbers wrong. These are RMS values given in the problem. Part C, the reactance of the coil. So we have this coil. The magnetizing current is given for this Vs and Is. You know that in this simple circuit, the magnetizing inductance for this inductor is equal to Vs divided by Is. Yes, so you can use peak values or RMS values. Must be the same, right? Format. So here we have RMS value of the Vs 120 divided by 5, the RMS value of the magnetizing current, that is equal to 24 ohm. This is the value of the magnetizing reactance. So this magnetizing reactance corresponds to this frequency, 60 Hertz. How we can calculate the inductance of the coil? You know that the magnetizing reactance is equal to omega L, magnetizing inductance, or equal to 2 times pi times F times Lm. We know the value of the frequency, that is 60 Hertz. So if you replace the numbers, the value, let me check, 24 divided by 2 times pi times 60 is equal to this one. If we multiply this by 1e3, it will be equal to 63.6 millihenries. So yes, this is the procedure to calculate these quantities for the coil. This is the case of actually a single phase transformer when we fed the primary coil to magnetize the structure. We have this magnetizing reactance in the equivalent circuit model of a transformer. So let's go for the next problem. Problem 6. A single phase 5 kilovolt ampere 240 volt 220 60 hertz transformer has a core loss of 100 watt at rated voltage and copper loss of 120 at rated current. So the value of the core loss at rated voltage is given. The value of the copper loss at rated current, or actually full load current, is given. Calculate the efficiency for the following load conditions. A, it is delivering 5 kilovolt ampere at rated voltage and a power factor of 0.8. B, it is delivering 2 kilovolt ampere at rated voltage and a power factor of 0.8. So what was the definition of the efficiency for a transformer? The efficiency of a transformer is defined as follows: the output power divided by the input power, the real power, right? Not reactive or kilovolt ampere, volt ampere. So the output power, right, is equal to V2 I2 times cosine of theta 2. Theta 2, right, is the angle for the load impedance. So here you can see the efficiency part, the part 2.4 of the second chapter. This is the definition of the efficiency. So the output power is equal to V2, the voltage of the secondary side, I2 times cosine of theta 2. The theta 2 is the load power factor. So this note is also important because the transformer is a static device. There are no rotational losses such as windage and friction losses in a rotating electric machine. In the case of rotating electric machines, we have mechanical loss, and also iron losses is also higher because we have rotating fluxes and so on, more complex than what we have in transformers. So in a well-designed transformer, the efficiency can be as high as 99%. Yes. So here is the definition, and we can write the efficiency is equal to the output power divided by the output power plus losses. We have core loss, PC, and we have copper loss. So finally, we can write this equation. The output power divided by the output power plus core loss plus copper loss. This equation. So you can replace the right corresponding values. For the P out, we have this. And what about the copper losses? Copper losses for the full load, right, is equal to this one, I1 to the power 2 R1 plus I2 to the power 2 R2, when I1 and I2 are actually equivalent to the full load operation of the transformer. Also, we can write this summation in to the following, right, equivalent equations. You know, we had these two equivalent models for transformers also. Our equivalent one is the referred equivalent resistance to side 1, and R equivalent to is the referred equivalent resistance to the side 2. So we have these equivalent calculations. So this equation, how we can extend it for any arbitrary power factor or load fraction. The value of the core loss depends on the rated voltage of the primary and secondary coils, right? You remember from the previous chapter we had a problem. Yes, let me show it from examples of the chapter 1. We had this problem. Yes, comparison of total core losses, hysteresis losses, and eddy current losses when we change the input voltage. So yes, in this example, for the part A and B, rated voltage, right? The voltage is the same as here, the number that we have core losses. So core losses, right, is the same for these two parts, and we can use this number. What about the copper losses? Copper losses depends on the load fraction. What is the load fraction? The load fraction is defined as the current, right, divided by the full load current. So this is secondary current I2, right? You can consider that, or is defined as the volt ampere of the transformer for a specific load fraction divided by the rated one. What is the rated value of the S? In our case is 5 kilovolt ampere. The rated value of the S for this transformer. So we will have this, the value of the copper losses, at a desired output current is equal to x to the power 2 times the value of copper losses for full load current. Press this fraction that we have here. So now let's calculate the efficiency for the part A. The transformer delivers 5 kilovolt ampere. What is the value of the output power? The real power is S out times the power factor. So this is 5 kilovolt ampere or 5000 volt ampere times 0.8, that is equal to 4000 watt. Also, you remember this power triangle. This is S, this is P, the real power, and this is Q, the reactive power. This is the angle theta. Cosine of theta is the power factor. And P is equal to S times cosine of theta. Q is equal to S times sine of theta. Okay. So we have these two equations. And I implemented this equation here. This is, right, 5000 times 0.8. So what is the value of the load fraction X is equal to the S divided by the rated one. So 5 kilovolt ampere divided by 5 kilovolt ampere, that is equal to 1. So this is corresponding to the full load case. If you replace the numbers, this is the output power, this one, the unit is watt, right? Consider this. Here, the unit of the core loss and copper loss is in watt. So you should use the same units when you calculate the efficiency using this equation. So finally, we will have 94.7%. For the part B, the transformer delivers 2 kilovolt ampere at the rated voltage and power factor 0.8. So we can repeat the calculations again. Here is the output power, 2000, right? 2000 volt ampere times 0.8 is 1600 watts. What is the value of the load fraction? Is 2 kilovolt ampere divided by the rated one, 5 kilovolt ampere, that is 0.4. So the value of the efficiency will be equal to this fraction, that is equal to 93%. So now let's generate a graph in MATLAB. I want to change the value of the load fraction and calculate the efficiency as a function of the load fraction. We had this curve in the reference, this one, efficiency of a transformer as a function of the load fraction, I2 divided by I2 rated. As you can see, when the load fraction is low, the efficiency is low. We have a maximum efficiency right here. And again, if we increase the load fraction, maybe overloading of the transformer, right, the efficiency could reduce. So we generate this graph now. Here is the efficiency. So we had also one important equation here, the fraction that we get the maximum efficiency. That is equal to SQRT of core loss divided by the copper loss for the full load current, this fraction. So we get the maximum efficiency for the transformer when the load fraction is equal to this one. And the load fraction for maximum efficiency does not depend on the value of the power factor of the load. Yes. So when we change the load power factor, the point, the load fraction that we get the maximum efficiency, right, is the same. So here, problem, let me write the problem 6. We have these inputs. The core loss is 100, this one. The copper loss for the full load current is 120. And this is S2, or let me write S rated. That is equal to 5000. The unit is volt ampere. And I considered the load power factor equal to 0.8 to calculate the efficiency. I changed the load fraction from 0.2 to 1. Let's consider 20% overload, 1.2. And here is the equation for calculation of the efficiency. So this is the rated value of the S times power factor times the fraction, the load fraction, and this is the denominator of the efficiency fraction, this one. So here we plot the efficiency versus the fraction, and using this command I find the location that we get the maximum efficiency. So let's run the code. Here you can see the efficiency versus the load fraction. So let's add the proper labels here. X label is the X that is equal to load fraction is equal to S divided by S rated. You know that. So yes, we can use this type of coding to write this right in this format. This is the load fraction. The y-axis is the efficiency. Y label is efficiency of the transformer. Yes. So here we have a maximum efficiency that is equal to 94.8%. What is the load fraction here that we get the maximum efficiency? Is equal to 0.91. Yes. So is equal to this one. Let's check. This is SQRT, the core loss divided by the rated value of the copper loss, the load fraction that we get the maximum efficiency. So here if I write SQRT of 100, that is the core loss divided by 120. 0.912. Yes, this point. You can remember, right, this important equation. Now let's check this point. Does the load fraction that we get the maximum efficiency for that depends on the load power factor or not? Here in this graph, as you can see, when we change the value of the load power factor, the efficiency changes, but the point that we get the maximum efficiency the load fraction that we get the maximum efficiency is the same. So how we can generate this graph? I can write a for loop here. For power factor equal to, let's iterate for these numbers, 0.6, 8, and 1. I want to iterate the value of the power factor on these three numbers. So this is the format of coding and end. So let's modify the indent. Okay. And now we can plot, run. Here you can see the curves, efficiency curves versus the power factor. Also, you can consider a legend for these curves. Here, as you can see, the points that we get the maximum efficiency, the load fraction, right, the same. And you can see the efficiency. This is important point that we can learn from this problem. Yes, the fraction that we get the maximum efficiency is independent of the power factor. So here, let me write, because when we generate plots, we need to consider a specific legend for each of them. If I highlight this, at the end of this for loop, we can write this legend. What was the value of the power factor for the first case? Equal to 0.6. For the second curve is equal to 0.8, and for the last one is equal to 1. So we can add this legend to the plot. The value of the power factor 0.6, 0.8, 1. Okay, so you can write a similar code here and practice this problem. Anyway, the next problem, problem 7, a single phase 1200 kilovolt ampere, 240 to 120 volt 60 hertz transformer has a no load loss of 3.2 kilowatt at rated voltage and a copper loss of 9.5 kilowatt at rated current. Determine the efficiency for the following load conditions. So this term, no load loss, is equivalent to this term, core loss. We know that the no load loss of a transformer is its core loss, right? So sometimes we might have different terms, no load loss or core loss. A. When the transformer delivers the rated kilovolt ampere at unity power factor. So we can use the same equations that we had for the previous problem and write S out times the power factor. This is the load fraction. X is equal to 1 for the part A. The efficiency is equal to 98.95. So when the power factor is 1, this is the efficiency. And in the second case, we have a lower power factor, 0.9. If we repeat the calculations, this is the value of the efficiency, 98, right, 0.8. And for the last case, C, this is the rated kilovolt ampere of the load, but the power factor is 0. When the value of the power factor is 0 is when we have pure L or C load, inductive or capacitive load. So in this case, the real output power is 0, and we don't have any real output power for inductive or capacitive loads. According to the definition of the efficiency will be equal to 0, right? Because the numerator is 0 here, but still we have these losses, core loss and copper loss. So what are points of this problem? The efficiency depends on real power, right? Not apparent or reactive power. Even at rated kilowatt ampere, if the power factor is poor, efficiency drops because you are still burning losses but not delivering real power. Yes, we saw it here. When we reduce the value of the power factor, the efficiency drops because the amount of loss is the same for a specific load fraction, but we are reducing the amount of the output power. So high current with low or zero power factor gives poor efficiency. In power systems where low power factor loads can waste energy and require power factor correction. Yes, in the power systems that the load power factor is low, we need to modify the power factor to actually increase the efficiency of the transformer. Otherwise, we have waste of energy. If you have this single phase transformer here and this load ZL, the efficiency of the transformer depends on the power factor of the load. As long as we can increase the power factor of the load, also we can increase the efficiency of the transformer. You remember from the electric circuit course, right? The electric circuit theory course, that how we can improve the power factor of a load, inductive load. We can add the capacitors, right? So this is why power factor correction is important to increase the overall efficiency of the power system transformers that we have in a power system. So you can review this problem and also review these important points of this problem. So let's go for the problem 8. A resistive load varies from 1 to zero point 0.5 ohm. So we have a varying load here, and the load is resistive. Here is the value of the R, and this is the range that the value of the R varies in it. The load is supplied by an AC generator through an ideal transformer whose turns ratio can be changed by using different tapes as shown in this figure. So let me copy this. Here we have this generator generates a single phase AC voltage. This is the load range, resistive load, and here is the inductor. This is right for this generator. I will explain it. So we have ideal transformer here, an ideal transformer that we can change the turns ratio by this tape. Yes. So this is the turns ratio A to 1. We know that A is equal to N1 divided by N2. The generator can be modeled as a constant voltage of 100 volt RMS value in series with an inductive reactance of 1 ohm. So this is for generator model, right? This side is model of the generator. One voltage source, constant voltage, and this inductor. So for maximum power transfer to the load, the effective load resistance seen at the transformer primary generator side must equal the series impedance of the generator, that is, the referred value of R to the primary side is always 1 ohm. So A. Determine the range of turns ratio for maximum power transfer to the load. B. Determine the range of load voltage for maximum power transfer. C. Determine the value of the power transferred. So you know we can refer the load to the primary side, perform calculations, and consider the maximum real power delivered, right? Considering these circuits that we have from electric circuit theory course, yes, for maximum real power delivered to this impedance Z2. So here, first let's transfer the load resistance to the primary. How we can transfer it? This is the problem. We have this ideal transformer, and this is the turns ratio. You remember from the chapter how we can transfer R to the primary side? This will be the equivalent circuit. This is the voltage, this reactance J1, and this is the value of R prime. This is the transformer, and here when we transfer the load, this will be short circuit here. This is the turns ratio. Or actually we can neglect this. Finally we have this circuit. This is the Vs source, the inductor, and this equivalent resistor R prime, that is equal to A to the power 2 times R. So we have this equivalent circuit equivalent to this one. Now we can use this slide, these equations, depending on the case that we have. You remember these conditions from the electric circuit course. When we have two impedances, Z1 and Z2, that are equal to R1 and R2, resistive loads. We don't have any inductive or capacitive components in Z1 and Z2. In this case, the maximum power is delivered to R2 when R1 is equal to R2. In this case, we have R1 plus JX1. We have both resistive and inductive, right, terms in Z1, but only resistive term for the load. So the maximum power condition is this one, the absolute value or amplitudinal Z1 must be equal to R2. In this case, we have Z1 and Z2, both resistive and inductive terms. So in this case, the Z1 must be equal to Z2 complex conjugate. Yes. And this final term is when we have JX1 but R2, this resistive load. The amplitude of the X1 must be equal to R2. This is our case, the case that we have here. So the maximum power is delivered to this load when the value of A2 times R is equal to 1. Yes, this equation. So we have this range for the resistance from 0.5 to 1. If we consider the value of the resistance equal to 1, the value of A will be equal to 1, turns ratio. And if we consider the value of R equal to 0.5, the value of the A will be equal to SQRT02 or 1.41. So this is the range of turns ratio from 1 to 1.41. The range of turns ratio for maximum power transfer to the load. Yes. Determine the range of load voltage for maximum power transfer. So, yes, how we can calculate the voltage here? What is the value of the current? I1 is equal to Vs divided by the amplitude, this one, A2 times R plus J1, the amplitude of this impedance, Z total. This is equal to SQRT02, right? Because we know that these two are equal. A2 times R is equal to 1. Yes, this is 1. And let me rewrite it. This is the value of I1 is equal to Vs divided by A2R plus J1. This is a complex number, right? This complex number, this is A2R that is equal to 1, and this is the imaginary part. The imaginary part, this is the real part. This is equal to 1. So this is the impedance, this one. What is the amplitude? Is equal to SQRT02. So the I1 will be equal to Vs divided by SQRTO2 that is equal to 70.7 amps. The value of the V1, the voltage on this element, the voltage on this element, okay, this is Vs, this is the inductor J1, this is the load. The value of the voltage here, V1, this voltage, is equal to I1 times A2 times R. Okay, so this is the value of the voltage, 70.7 volt. How we can transfer this to the secondary side? We should divide it by the turns ratio. Yes. So the value of the V2 in here, in this case, we calculated voltage of the secondary part, but the value of the voltage here, V2 is equal to V1 divided by A. Okay, so in this case, the value of the V2 will be equal to 70.7 when the value of A is equal to 1, and will be equal to 50 when the value of the A is equal to 1.41. So this is the range of the output voltage if we are going to get the maximum power. C, determine the power transferred. Yes, this is the value of the power R prime times I1 to the power 2. If you replace the numbers, we will have this amount of the power, 5 kilowatt. So let's solve this problem in Simplorer to practice it in the ANSYS Simplorer software. Problem 8. So let's rename this to problem 8, and let's add this transformer from circuits. We can use this two winding transformer, this ideal one. Okay, also we have this resistive load R. Okay, let's do this connection and this connection. This inductor we have. Okay, the value of the inductor is 1 Henry. Yes, J1. Excuse me, this is the reactance. We need to set the inductance here. This circuit is for, we don't have the value of the frequency here, right? The frequency is not given here. We need that to calculate the value of the inductance. Let's consider the value of the frequency equal to 60 hertz. Okay, so the value of the inductance will be equal to 1 divided by 2 times pi times 60. This equation, I think we can consider it here also. Yes, this is the value of the inductance. And finally, the voltage of the generator is equal to time controlled sine. The RMS value is 100. Okay, so, and let's add this ground. Here we can define two parameters. I want to define one parameter here. This is R, or this is our load, the resistance of the load. Press enter. What is the value? Let's consider equal to 1 ohm. Okay. And here we have this parameter, turns ratio. So I define A. This is, in this case, this is N2 divided by N1. Differs from the definition that we have here in this reference. So I define it as 1 divided by, this is the turns ratio. Let's consider it equal to this number, 1. Okay. Okay. So also I want to measure the value of the load power. So we can add a wattmeter here. So let's delete these wires and add from the measurement this one. Okay, this is the load current and this is the load voltage. Yes, so also we can add the ground to the secondary side. Let's add the analysis setup. Like before, we need the AC solver 50 and 60. Just solve the problem for these two cases. Analyze. I want to check the data table, the value of the current of the L1. Let's check I1 first. Yes, we have this number for 60 Hertz. Let's check the values. When the value of R is equal to 1, the turns ratio is equal to, will be equal to 1. So here, when we set the value of the A equal to 1, this is the load. Yes, and this is the value of the current. Here we have decibel function. We need to delete this, apply. And let's show it in magnitude and phase. From here, tools, options, you can set the default, right? Options, when you generate this report, a table, you can set the precision. Yes. And what about the curve or marks? General. I don't want to have a decibel function every time that we generate the report. Maybe you can check it from these settings that we have here. Anyway, so here is the value of the current, 700.7, and this is the angle of the I1. Also, let's add the power, new report. This is the value of the power, 5 kilowatt. Yes, as we calculated it here, 5 kilowatt. Okay, so now let's do a parametric analysis. I want to change the value of the load resistance. Okay, the value of the load resistance and calculate the load power. Fixing the value of the turns ratio. Just I want to generate this graph for our problem. We know that when the value of the A is equal to 1, yes, the maximum power is delivered to the load for R equal to 1. So if we change the value of the R, for example, in this range from 0.5 to 1.5, the maximum power should occur at R equal to 1, right? According to our calculations. So how we can do this parametric analysis in the ANSYS Simplorer? So here I defined one parametric analysis before. So if we define it again, we have this AC solver from here, parametric setup. Let's add this variable R load. I want to change it from 0.5 to 1.5. The step size 0.05. Okay, this is the calculation table. We change the value of the load resistance from 0.5 ohm to 1.5 ohm. And here is the analysis setup used by this parametric sweep. So we can overwrite these values for a starting point. We don't need to check this. And here we save solutions to the database to be able to generate the plot. This is parametric setup. Let's change its name to R load. We are going to change the value of the R load. So if I analyze this parametric setup, here we have 20 simulations. Simulation is done. Now we can generate this rectangle plot. So this is the load power. Let's generate the graph for the real part. The real part of the power is the active power. So here, this graph is the power versus frequency. I need to select the parametric setup one. As you can see, x-axis is frequency, and we calculated the power for different values of the R load. We don't need this graph. We need to set the primary sweep equal to the load resistance. Okay, the parametric analysis, and this is the primary sweep. Generate a new report. Here you can see this graph when the frequency is 60 Hz and when the frequency is 50 Hz. I don't need that frequency, so just select 60. Okay, so this is the graph. We did our calculations using 60 Hz, right? When we set the value of the L1 inductance. So this is the graph. Here, let's add this X marker. As you can see, The maximum power is delivered to the load when the load resistance is 1 ohm. What is the maximum value? 5 kilowatt. Yes, you can generate this beautiful graph in ANSYS Simplorer. So how the ANSYS Simplorer powerful is, we can do this kind of parametric simulations in the software to generate this graph and verify our calculations. Perfect. So now let's go for the next problem. Problem 9. A single phase two winding transformer has 1000 turns on the primary and 500 turns on the secondary. The primary winding is connected to a 220 volt supply and the secondary winding is connected to a 5 kilovolt ampere load. The transformer can be considered ideal. A. Determine the load voltage. B. Determine the load impedance. C. Determine the load impedance referred to the primary. So here is the case, the circuit for this problem. We have this ideal transformer, the number of turns N1 is 1000, N2 is 500. This is the supply voltage. Here is the load impedance. A. Determine the load voltage. We know that V2 divided by V1 for ideal transformer is equal to N2 divided by N1. So V2 is equal to 500 divided by 1000 times 220. That is equal to 110 volt. This is the V2. What is the value of the I2? The current in the secondary is equal to the kilovolt ampere of the load divided by the V2. So what is the value of the volt ampere? Is 5 kilovolt ampere or 5000 volt ampere. So 5000 divided by 110 is equal to 45.45. So what is the value of the load impedance? The amplitude of Z load is equal to V2 divided by I2. That is equal to 110 divided by 45.45. That is equal to 2.42 ohm. This is the value of the Z load. How we can transfer it to the primary? Using this equation. Yes. So let me copy this. Here you can remember this pattern. Okay. When you want to transfer load impedance from this side to this side, first you should look at this number of terms, then this one. So Z prime is Z times N1 divided by N2 to the power 2, right? You first should look at this number of turns that you are going to transfer. And if you are going to transfer in this direction, so it will be equal to Z prime. Z, first look at this number, N2 divided by N1 to the power 2. So we have this equation, and you can replace the numbers, right? Z prime is equal to the Z load times n1 divided by n2 to the power 2. If you replace the numbers, the value will be equal to 9.68. Okay, so this is the part C. Okay, so let's review derivation of this equation for practice, right? How we can derive this equation. You remember we have this case. Consider this source V1 and this ideal transformer. This is the ZL. So here we have I1, this is I2, and here we have V2. Okay, so the value of the current I1 in this case must be the same as the value of the I1 for this case. V1, this is I1. I write a star here. This is the second, right, case that we have this circuit. This is ideal transformer, and this is actually short circuit when we transfer ZL here. So this is ZL star. So how much is the value of the voltage here in this case? Because the value of V2 star is equal to 0. The value right here is 0. The value of the current I1 star is equal to V1 star divided by ZL star. So in this case, the value of I1 is equal to, we need to consider turns ratio here. Okay, so what is the turns ratio? Is equal to I2 times N2 divided by N1. So this equal to this one. Here we have V1 star. Okay, and what is the value of the V1 star? We need to consider V2 here in this equation. Okay, so we can write V1 is equal to V2 times N1 divided by N2. So we have this current equation, this voltage equation for ideal transformer, and we have this case. So how we can satisfy this condition? This must be equal to this one, right? So we can write V1 star divided by ZL star. This must be equal to I2 divided by N1 times N2. This is equal to, we can consider this now. Let me cut this here. The value of the I2 is equal to, we have this ZL is equal V2 divided by I2. So I2 is equal to V2 divided by ZL. So this is V2 N2 ZL N1. What is the value of V2? Is equal to V1 N2 divided by N1. So this is N2 to the power 2, N1 to the power 2, ZL. In these two cases, these are equivalent. Yes, we know that V1 is equal to V1 star. Finally, we have these two terms, and we can write this. We can write this ZL times N1 divided by N2 to the power 2 is equal to ZL star, right? The value of the load impedance transferred to the primary side. So you can rewrite these equations and practice to understand how the transformation occurs, right? And how we calculated the value of the Z prime. Okay, so I think this is enough for today, and let's continue in the next video. Thanks for watching.